said, I'm a research fellow at the CBU, and today I'll talk a little bit about susceptibility artifacts in fMRI and ways that we can try to alleviate some of them. And so here's an outline of the talk. So I'll first just talk very briefly about what the problem is, how this can lead to potential reporting biases in the literature, and then some methodological adjustments we've made to fMRI sequences that can try to overcome some of the problems, and then what we're currently doing at the CBU. I should also say I gave a longer version of this talk at a previous methods days, and that's all available online. So, you know, if you want some more information, please do seek that out as well. So,
your head's cut off on Zoom.
Oh, is it?
Or angle the camera up a bit.
Sorry. Can that go up?
There you go.
Yeah, there we go. So great. So, many of you may already run fMRI experiments, and the implicit assumption is, you know, we're measuring sort of neural activity in the brain. What's quite important that maybe not everyone's aware of is the fMRI signal across the brain is not sampled evenly. And it's particularly affected in areas that are affected by what's called magnetic susceptibility artifacts. And it's essentially related to the fact that the magnetic field is not homogeneous when you put a person's head in the scanner. And this can lead to signal displacement and distortion, as shown in this figure on the left here by the signal buildup, or signal loss, shown by the figure in the right. You can see these dark patches. And I won't go into the technical details behind the reasons why, but it's essentially related to what's called a T2 star decay. So this is the measure that we use for bulb activation. And in brief, what happens is when you have a radiofrequency pulse at the beginning of each TR, or image volume collection, you have maximal signal, and that decays rapidly. And most fMRI studies are interested in the difference between two tasks. So essentially what you want to maximize is the difference between a control task and an experimental task. And so you collect an image volume at a certain delay in milliseconds, typically called the echo time, or TE. And you want to maximize the contrast between these two. But as you can see, the longer you leave it, the signal essentially starts to decay and is lost. And so it's a bit of a balance between when you collect this image, as opposed to when you may not actually have any signal measurements to detect. And so just to give you a concrete example, so here's some sort of raw fMRI signal data for two different EPI sequences. So here you can see at the bottom in this sort of jet color, the signal for a fMRI image at 30 milliseconds. And hopefully you can see there's this area of dropout in the orbitofrontal cortex and lateral temporal cortices. But at 12 milliseconds, the signal, of course, is higher because it's collected earlier in the T2 star decay. And you do still, even though it's weaker, you do get signal in the areas that are lost at 30 milliseconds. And again, to make this a bit more concrete, you can measure T2 star decay values in the brain using particular sequences. So what I've plotted here at the bottom are the optimal T2 star timings for each voxel. And interestingly, just to point out, you know, most of the studies that use fMRI sequences use an echo time of about 35 milliseconds, so this cyan to green color. And hopefully you can see, even in this data set that we collected at the CBU, the majority of the areas of the brain don't really fall around that window. In fact, a lot of them have echo times that are slightly higher. And then, of course, you get these areas of susceptibility artifacts, which are much lower, around the 10 millisecond range. And so just to give you a concrete example from my own line of research, how this can affect the literature at large. So there's a lot of converging evidence for the role of semantic cognition. So this is how we make meaning of objects and knowledge in the world. And that's centered around the anterior and inferior temporal lobes. So there's various studies using PET imaging data, using neuropsychology, TMS perturbations, MEG. I won't go into all of the details, but there's a distinct lack, or there has been, at least up until the last decade, lack of evidence from fMRI. And rightly or wrongly, fMRI results are very overemphasized in the literature, so they affect meta-analyses, how we develop theoretical models. And so just to give you an example, so here on the left is a language model by Kathy Price. I won't go into any of the details, but just to sort of point out this area here in the ventral anterior temporal lobes, there's just no information or meaning mapped to it. This model from our own director at the CBU, Matt Lambon-Ralph, so they have incorporated in the last decade methods to overcome some of these problems, and they have included ventral anterior temporal lobe areas in their theoretical models. It's also important to say it's not just these sort of a priori models that can be affected. There's a lot of studies now that run data-driven analyses. So this is a popular ROI atlas by the Power Group. And hopefully, it's a bit hard to see, but hopefully you can see the ventral parts of the temporal lobe and orbitofrontal cortices are missing. So it can also affect analyses that you're interested in that don't have any a priori models. And so as I talked about in the beginning, so you do have this distortion. There are strategies, sort of post hoc correction strategies you can apply to correct for this. So field map correction, reverse split correction. I won't be talking about those specifically today. I'll talk a little bit more about the signal loss. And so there's a number of researchers who have come up with various strategies you can do sort of before or during scanning. These have small but significant improvements. And there's an updated publication by the Weisskopf group last year. So what we did when we were at Manchester was we developed a spin echo fMRI sequence. I won't go into the details of the protocol, but essentially we showed it across numerous publications that you get very robust ventral anterior temporal lobe activation when we put participants in the scanner to do semantic tasks. But it's been known in the field for a long time that spin echo sequence has low signal to noise compared to what's typically used, which is gradient echo scanning. So some work that I did during my PhD was to compare spin echo and dual gradient echo. And we showed, again, across areas in the brain that the dual gradient echo was significantly better than the spin echo in all areas related to semantics except for the cerebellum. And since then, there's been sort of more research done using Multiecho, and what's done in the field is they collect more than 3 or 4 echoes at a time. So hopefully you can see this figure quite clearly. So you've got on the first row the 3 Tesla data and 7 Tesla data at different echo times, and the combination at the end tries to sort of recover some of this lost signal. And there's been advances in denoising algorithms. So there's this review paper by Prantik Kundu, here in 2017. And there's a whole toolkit now developed to essentially, you can apply to any data collected, which uses independent component analysis to classify whether signal in the data is more reflective of what you would expect from bold activation or artifacts. And so the current work at the CBU, so there are various methodological issues with some of the work that has been done. So Marta, Rick, and I started to collect our own data at the CBU, where we wanted to essentially directly compare a standard sequence that many researchers at the CBU and beyond use with modifications. And so we built a factorial design where we manipulated echo and also multi-banding. I haven't talked about that, but that has also been shown to affect signal quality as well. And so we put participants in the scanner, gave them a semantic task. And I won't go into all of the details because I'm due to give an IIG talk in where I will spend a lot more time discussing the details. But just to show you a snippet of the results, so here I'm showing you the semantic effect for the single echo, single band, single echo, multi-band, multi-echo, single band, and multi-echo, multi-band. And what's quite pleasing, actually, is across all of the different methods, you get activation going all the way into the ventral anterior temporal lobes to some degree. We've done various analyses where we've compared the method. We've compared them directly. But like I said, I'll be able to speak about that at more detail at an IIG in the near future. And importantly, we're also replicating this study at 7 Tesla. So Saskia Frisbee, who's a second-year PhD student, is leading that work. And we're very interested to see how well we can recover signal in the ventral anterior temporal lobes, because at 7 Tesla, the signal loss problem is exacerbated. And we've just finished a pilot study where we have seen some hints of signal, so we're actually quite surprised that we could get any. So that was quite, it was pretty interesting for us. So just to end, as I was saying, we shouldn't expect good signal everywhere in the brain. There are methods to overcome this. We originally, in our group, were using spin echo fMRI, but now we've moved to a gradient echo multi-band sequence, which we think is potentially improved sensitivity. And important for the research community locally, we have protocols that we've implemented at the CBU and the WIVIC. So if anybody's interested, please do reach out to Marta or myself. And important that everyone should really be checking their data very routinely. As I showed you from the early slides, sometimes you see things that you may not always be aware of. And that's everything. Thanks, everyone.